Okay, so this is something I've actually spoken about before, but I wanted to just have a really tight 1 or 2 minute version of lying around on video so I could reference people because it's such a common question that comes up when we're talking about mitigating side channels. So I work on side channels and side channel research and securing systems and keeping them secure against side channels. And a common kind of side channel is a timing side channel, right? And I'm not going to go too deep into types of side channels, but like, or types of timing side channels, but just a really simple illustration is like, imagine you've got an operation that takes different amounts of time for different people, right? So one person does it and it takes, say, 10 milliseconds. Another person does it and it takes them 20 milliseconds. Another person does it, it takes them 15 milliseconds. And then another person does it, and it takes like 25 milliseconds, say, something really slow, right? Well, an outside observer who can maybe just see how long these operations take can see whose operation is being done, right? They can just measure the time and they go, okay, well, an operation occurred here and it took 25 milliseconds, so that's this pink one, right? Easy peasy. We derive some information that we shouldn't know just by measuring timing, right? In reality, this comes about through, effects that might happen inside systems like caching or compression and so on. But whenever we encounter these timing side channels, there's always someone in the room who's like, okay, aha, what if we added jitter? Then I wouldn't have to worry about this so much, right? And so let's just pick two of these, for example. Let's take the pink one and the green one and look at what happens if we add jitter, right? And so let's say, uh, here's our starting positions, right? This is how long they take naturally. And let's say we add just a uniformly random amount of jitter, right? So let's say we add another, I don't know, 100 milliseconds of jitter, and every potential value of jitter has equal probability. So then what happens is, well, we add an artificial amount of delay between 0 and 100 milliseconds, and now the graphs um, will look like this, right? And so this operation took, what is it, 10 milliseconds here. So the fastest it could possibly execute is actually here, and the slowest it could possibly execute is here, right? And this one took 25 organically, so the fastest it could possibly execute is here, and the slowest it could possibly execute is here, right? And you can straight away probably see the problem, which is now from measuring what's going on, right? From the outside observer, if I see a measurement in either this region here, right, or this region here, I can tell which it was, right? Because if I see a measurement in this region here, I know for sure it was green. And if I see a measurement over here, I know for sure it was pink. Simple as that, right? So that's why adding a uniformly random amount of jitter doesn't really work. In fact, it just increases attacker difficulty by kind of a linear power, right? However much jitter you add, they're just going to have to do more measurements, and eventually they'll get a measurement that's in one or two of these zones, right? It doesn't work. That's why jitter doesn't work. But then the next, that person's really clever. Thinking of jitter is not too obvious, right? And then their next kind of objection is like, well, this I'm only getting defeated because you're detecting these measurements in the kind of outlier regions. So what if I add non-uniform jitter that's kind of more likely to land in the regions where there's overlap, right? Then you're not going to be able. Then I'm going to outsmart you, right? So let's graph that and see what happens, right? So again, we're going to have our short green line and our slightly longer pink line. And so this time, let's try to add a non-uniform amount of jitter that's kind of less likely around the beginning and the end zones, right? Because that's what we're worried about. So let's say it peaks up like this, like almost like a normal distribution, say, and goes down here, right? And let's say we do the same over here. So we add a non-uniform amount of jitter. So I'm just kind of representing the likelihood of the data points here with these. I can do a great job of picturing these. But the problem now is actually, although you might think this is better, right? Because now if the attacker gets a measurement, right? And let's say they do a measurement and they get this value here, right? Well, they can't tell whether that was pink or green. That's true. That's just like before, when we had the uniform kind of linear, jitter or noise being added, right? If they land in here, they can't tell which is which, right? But this is not a game of just doing things one at a time. We're doing it many, many times. And in this model, well, you just got to go enough times until you eventually get one of these data points, right? And that's how the attacker wins. But in this game, there are more ways to win. The attacker wins. Well, okay, just like before, they win if they get a data point in here, and they win if they get a data point over here, right? That's just like before. But we've reduced we've reduced the likelihood of them ever getting a data point in there because there's just more data points in the middle, right? So you think, oh, we're making life harder for the attacker. Actually, we've made life significantly easier for the attacker because there's a shape to this noise and jitter. As they get data points, they can actually figure out which curve they got, and in far fewer data points, way fewer data points, they can start to get a feel for the shape of the line, right? Or the shape of the noise that's been added, and whether it's this one or whether it's this one, right? And so they can kind of reverse engineer from there and figure out, okay, again, I know whether it was green or whether it was pink. And this is actually a really good example of being too clever for your own good, right? Like you can see how someone smarter goes, okay, well, first adding noise, that's going to defeat the attacker, but really it only makes life a little bit harder for the attacker because of this property. And then they're smarter still and they go, well, let's make this overlap region more likely, right? Well, actually that creates a shape to your data distribution. And any shape, doesn't have to be this shape, doesn't have to be a normal distribution, any shape will be something they can profile, and actually you actually made life easier for the attacker than the uniform case, right? So the uniform case is the best you can do with noise. But as you can see, neither really work. The attacker can still figure out which is which. And so what do they have to do? Well, the only real robust solution is actually to make everything take the same amount of time, no matter what, right? So you take your worst case. So in this case, it's the pink value, right? And then if the green value was something you processed, then you add some noise or jitter or delay or whatever until the green operation takes just as long as the pink operation, right? And the blue, you do the same. And do I even have that original color? I think it's this one. Right? And so now by adding padding, this is generally called, by padding up to what's called the blinding value, or the same, where they all appear to take the same amount of time, only then will the attacker not be able to tell through timing which operation was which. Of course, in many systems, making every operation take the exact same amount of time can be very cumbersome and hard to do. But that is what is at the heart of constant time operations when we're talking about that in the context of cryptography. So that's a whole important aspect of cryptographic engineering for preventing side channels. And that's what's going on. So hopefully, this ended up being more than a tight 1 or 2 minutes. But hopefully this explanation will help you understand why you can't just take a side channel and add either a uniform amount of noise or a non-uniform amount of noise and really defeat the attacker. You instead have to pad every operation to the same length. Now, of course, you can make life significantly difficult for attackers in some cases. In F2N, our cryptography library here at Amazon, we actually add a uniform amount of noise to every error case, just on the chance that there might be a side channel exposed in that error. Um, without any other reason, without any actual belief that there is a side channel there, just as another layer of defense in depth, we do it. But the amount of noise we add is gigantic. So we add up to 30 seconds of noise, granular to nanoseconds. So the amount of measurements an attacker would have to do to find either of these regions on a reasonably sized side channel, like a side channel that is also measured in nanoseconds, would be trillions, hundreds of billions to trillions. So it significantly raises the attacker difficulty. Not to the same magnitude as like cryptographic security. Trillions is not the security level you'd expect of robust cryptography primitive, but it's still real world significant and would thwart any real world attacker in my opinion. So it can still be a useful approach, still very useful to do. If you add a lot of noise, like a huge amount of jitter in the face of some possible side channel, but in general, it doesn't work, and you have to do constant time. All right, there you go. I didn't expect to have any viewers, but we have a question. What about the power consumption or cooling of the hardware? Could that be used as a side channel? There's a lot of modern side channel research on that, where folks tap the power feeds into a processor or chip and see if they can determine any difference in power utilization based on the data. And there have definitely been papers published where people have been able to figure that out. There's also things like Tempest Attacks, where you use electromagnetic field interference to do the same, to figure out what's on somebody's screen, say. All of those attacks need physical proximity and tend to be only useful in fairly esoteric threat models. Like, for example, let's say you've got a security USB key, and you want to figure out what the key is inside the key. The cryptographic key is inside the thumb drive or whatever, and you shouldn't have access to it, but you have physical possession of it. So maybe you open it up and get out your oscilloscope or multimeter, and a multimeter won't do the job, but an oscilloscope might, and see if you can use the key tons of times with some known inputs, see what the power draws are on different pins, and eventually reverse engineer your way back to what the value might be, and so on. But kind of sci-fi stuff. Cool. Thanks for watching. That was my tight few minutes at least on side channels and jitter and how they work. I'm sure we'll see what people think.